Welcome to my second tutorial in statistical thinking titled Basic Concepts. We will begin with the question, what is data? According to Wikipedia, data are individual units of information. A datum describes a single quality or quantity of some object or phenomenon. Put more simply, we can say that data are pieces of information that have meaning attached. We imbue the data with meaning. For example, the number 195 has no meaning until we say it is someone's LDL or bad cholesterol level. However, it is only when we are presented with normal ranges for LDL cholesterol that the number 195 has real meaning to us. It is a very high level of bad cholesterol. A variable is the name given to a particular data type that varies from individual to individual. For example, ages, heights, weights, cholesterol levels for a group of individuals in a study are all variables. This brings us to the question, what is statistical thinking? If I were to choose one word to describe what is statistical thinking, that word would be variation. Statistical thinking is about understanding the variation in the world around us, how to measure, minimize, and reason with variation in order to make good decisions. Statistics, the discipline, is not a branch of mathematics. It is the application of math to data in order to turn data into meaningful information. The mathematical theories and calculations provide us with a framework or structure to reason with the variation in measurements. We reason with the variation in measurements within the mathematical framework in order to make good statistical decisions. As we will see throughout my tutorials, we don't need a whole lot of math skills to become a good and rigorous statistical thinker. The computer software can take care of the math for us so that we can focus on the statistical thinking behind the mathematical calculations. Statistical thinking begins with the observation that leads to the question about how we think the world may or may not work. Great scientists, like great artists, observe the world around them and ask thoughtful and insightful questions. These are questions about truth, the truth in a population of interest. There is great power in observation and taking the time to ask the right questions. In 1962, a 22-year-old named Bob Dylan asked 9 quantitative questions about the world around him. He was an astute observer with a very curious mind. His way with words enabled him to ask very powerful questions. The first quantitative question he asked in the song titled Blowing in the Wind was, how many roads must a man walk down before you call him a man? Almost 60 years later, this is still a very powerful question, and one we still have not managed to answer. Good statistical thinking begins with the question, and then it is our job to pursue an answer to the question as best we can, using statistical analysis. Though Bob Dylan's answer was an insightful one from a poet's point of view, we will reason to answers to our questions that are more concrete and grounded in data and scientific thinking. However, we will see that our answers still contain a certain element of mystery, because the truth, as stated in our last tutorial, is impossible to pin down in any absolute sense. Our job is to learn how to reason with the uncertainty regarding what the truth may be. When we observe the world around us, we see that variation is everywhere. We as individuals vary in countless different ways. We vary in age, height, weight, gender, blood pressure, race, eye color, hair color, arm and leg length, waist size, hand and foot size, skin color, head, nose and ear size, cholesterol level, heart rate, anxiety, depression, happiness, and joy. Evolution has resulted in making each one of us a very unique and complex individual. We vary in everything we do, how much we sleep, how much we study, exercise, time spent on social media, time with friends, how much we walk, talk, think, read, and listen, how much we buy, what we buy, the movies we watch, what food we eat, how much we eat, our likes and dislikes, how much we drink, smoke, laugh, cry, dance, and sing. At the heart of statistical thinking is the need to understand variation. What we are even more interested in is the relationship between variables. How, say, 2 or more variables vary together. Here is a list of research topics my students have shown interest in the past. The effects of sleep on academic performance, exercise and productivity, alcohol drug use, and academic success, to name a few examples. We are all interested in what causes what. As we learn, trying to determine cause and effect relationships is at the heart of statistical thinking. The world of observational data is complex. For example, individuals will vary in their response to the same treatment for lowering cholesterol for many different reasons. Some of the reasons are differences in what we eat, how much we exercise, whether we smoke or not, how overweight we are, or how much alcohol we drink. Researchers might be interested in knowing how effective their treatment is at lowering cholesterol levels. The question is, how do the researchers know whether their treatment or some other variable or characteristic about the individual caused the reduction in cholesterol? This is where the power of statistical thinking comes into play. The type of study that enables us to find answers to these type of questions is known as a randomized experiment, often called the gold standard in research. A properly conducted, well-designed randomized experiment has the power to allow us to make causal conclusions about the effectiveness of a drug. For example, we can take 100 patients and randomly assign 50 of them to Crestor, a treatment for lowering cholesterol, and 50 to placebo, a type of dummy drug. Random assignment simply means that each patient is equally likely to be assigned to either treatment. Random assignment has the power to remove or average out the effects of any other factors on cholesterol level across the two groups. This means that subjects assigned to either Crestor or placebo should, or are expected to, be approximately the same average age, weight, height, and so on. There should be approximately the same proportion of patients who smoke, drink alcohol, and exercise on the treatment and on the placebo. After random assignment is completed, all factors that might affect the patient's cholesterol levels should be averaged out of the way. This process enables us to see clearly the effect of the treatment on cholesterol level. If we find that the average cholesterol level is statistically significantly lower for patients on Crestor compared to patients on placebo, then we can say the difference is most likely due to Crestor. Random assignment is a very powerful technique. However, it does not eliminate all the uncertainty in our decision making. When we say the results of our randomized experiment are statistically significant, we are simply stating that given the average difference in cholesterol levels we found between the sample groups, there is a very small chance that Crestor would not be effective if the treatment were given to everyone in the population. Therefore, based on the statistical evidence found in our sample data, we decide that the treatment is effective. However, it does not mean we definitely made the right decision. Why are we still uncertain as to whether we made the right decision about the effectiveness of the drug? The uncertainty remains because we only used a sample of 100 subjects with high cholesterol out of a much larger population of people with high cholesterol. The sample only gives us an estimate of the average effect of the drug in the entire population, and different samples will result in different sample averages, all estimates of the same population effect. This concept is known as sampling variation, and it is the most challenging concept at the heart of statistical thinking. Sample statistics vary from sample to sample. Our aim is to try to minimize the distance of our sample statistic, for example, the sample mean cholesterol level for patients on Crestor, from the unknown population parameter, population mean cholesterol, if everyone in the population with high cholesterol were put on Crestor. Understanding variation in individual measurements and in sample statistics are core foundational concepts at the heart of statistical thinking. In our next tutorial, we'll begin to learn how to reason with the variation in individual measurements.